Hello my friends, in this video I will solve two problems related to AC currents, and one is about how we transmit the AC electricity through transmission lines and why we want to transmit them at high voltage. We talked about this theoretically, saying that if we transmit them at high voltages we will lose less energy, so less power will be dissipated through the transmission lines, and this question is showing us that numerically and proving that it is the case. So here's the question: to provide power to a small city, a power plant generates 40 megawatt of AC electricity. So that's the power, right? So this is the initially generated power at a power plant, 40 megawatt. Mega is 10 to 6 or million, so it's 40, not 10. It's 40 times 10 to 6 or 40 million watts. The power plant is 50 kilometers from the city at the typical distance, and 100 kilometers of wire is used in transmission line. This is an extra information. And this transmission line is quite long, so they have a bit of resistance. Although they are wires low resistance, they still have a bit of resistance, and that resistance is about 7 ohms. So here is our situation. We have a power plant and we are sending power to homes, right? Here the initial power is this 40 megawatts, and the power lines has some resistance, which is 7 ohms. A tells us to provide 40 megawatt of power at the generator voltage of 25 volt. What the current is required. So we want 25,000 volt here at the generator. And we will send those to home. There will be a current generated through the wire. What is that current? This is simple Ohm's law, or we can use power to calculate the current, because we know power is equal to current times potential, and current is equal to power over the potential. So this is how much current is provided from the plant, right? And it will be passing through this line here, passing through this resistor. Alright, so power is 40 times 10 to 6 watts. That's the SI unit for power, and that's divided by a volt, 25,000 volt, and that should give me a current in ampere, and that current would be 1600 ampere. That's quite a bit of current, and that's part A. What is that current? Part B is asking us what is the power dissipated in the resistance of the transmission line for this current. So that would be the power we lose, the energy we lose throughout the transmission lines. And we can easily calculate that, right? We know current, we know resistance. Power is equal to also I squared R. We have this equation. So 1600 amperes squared times 7 ohms is our answer here, and this power will be 17.9 times 10 to 6 watt. That's 17.9 million watts, or about 18 million watts. This would be also equal to 17.9 megawatts. So quite a bit of loss here. If we initially transmit these with the potential difference of 25,000. Remember we talked about how we have transformers here to change the potential from the plant, higher it. The higher potential is better, right? And also when we give them to our homes, we have transformers to decrease the voltage down so we can use them for our devices. So if we use transformers to change the potential generated at the power plant to be 25,000 volts, we lose 17.9 megawatt of power that we generated, which was 40 megawatt. This is quite a bit of loss. Now the second part, C and D is asking us, how about if we increase the voltage we transmit the power? So to provide, C says to provide 40 megawatt of power at 500,000 volt, what is the current? And D, as you might have guessed, will ask, well, how much power is dissipated now through the resistance. So we'll do that. What is the current? If the transmission voltage is 500,000 volt, what is the current required? And we will use again P is equal to IV and I is equal to P power over voltage V. Initial generated power is still same, 40 megawatt divided by 500,000 volt. That's times 10 to 6. I'm leaving that there shortly. And the answer we get from here will be 80 amperes. Quite a bit lower than 1600 amperes we have. So as you might have guessed, how much power will be dissipated across the resistor will be also less. So power dissipated now, again, I squared R 80 amperes squared times 7 ohms, and that should give us a current of about power of about 44,800 watts. Now if we want to convert this to megawatt, we can rewrite it in this fashion: 0.0448 megawatt. That would be, so if you go step back, 1, 2, 3, 4, 5, 6, then that's times 10 to 6. Let me show you that. I don't want to jump here directly. Since I'm going 6 steps backward, I'm simply rewriting this as a power of 6, 10 to 6, to be able to convert to megawatt. You can also use a regular conversion method. So this number is equal to that. That means it's 0.0448 or about 0.0445 megawatt. A lot less than the one we found when we are transmitting with a lower voltage. So lower voltage causes higher current due to this relation here, and higher current causes more dissipation across the wires, which has some amount of resistance, and higher voltage causes less current as we transmit the electricity, and less current, less power lost through the transmission line. So that says why we have transformers to increase the voltage to a very high volt and then decrease it back, of course, to use it in our homes. This question is about transformers. A microscope illuminator uses a transformer to step down 120 volt AC. I'm going to try to draw a figure here. Here is how we represent transformers in a circuit. We are providing the primary a voltage that would be V1, and that's equal to 120 volt, and the secondary. What we're doing here is a step down. The secondary, this one has N1 turns, this one has N2 turns. N2 will be less than N1, but symbolically I'm showing them, so it's not represented in the figure here. So we step this down, this voltage. Remember, as the voltage changes here on the primary part, primary coil, there will be voltage induced in here. What will be induced? V2 will be induced, right? Induced EMF. And thus current 2 will be induced as well. And we have equations for relating those. We'll get to those. So here is the situation. We step it down to a wall outlet. So this is the wall outlet. I'm just putting something here, maybe a resistance, something. We are lighting up a light bulb and so on. Microscope bulb actually. Of power, to power a 12 volt 50 watt microscope. So 12 volts would be our V2. And the power this guy uses, dissipates, is 50 watt. Alright, that's the information we have. We are stepping down this voltage from 120 to 12 to be able to use it for this device. And as you remember, hopefully, this was the adapters we used. So all the adapters we use for our devices actually are transformers, stepping down the high voltage to be able to make them appropriate for our devices so they will not burn out. A, what is the resistance of the bulb filament? Right? I can use any information I have to calculate it. If I have enough information, I can use Ohm's law. Delta V over R. That would be my V2. That would be my I2. But I don't know I2, so I can't go with this. But I know power, and I know the potential difference. Power is equal to delta V squared over R. I have this information, and I have everybody here. I know delta V will be V2, so this will be V2 squared, and I know power. That would be actually P2. Let's call this also P2. So from here I can solve for resistance. Simply I can switch these guys algebraically, all correct. R will be equal to V2 squared over the power. 12 volt, square that, divided by 50 watt. Everybody is an SI unit, so I'm gonna get a resistance of a SI unit, which will be 2.88 ohms. Alright, that's what the resistance is. B, what RMS current in the bulb filament? What is the RMS current in the bulb filament? Alright, now I can use Ohm's law. I2 is equal to V2 over R. And I know everybody here, so I'll just put them in. 12 volts divided by 2.88 ohms, and that should be about 4.17 amperes. That's my I2. C, what is the RMS current in the primary coil? Now I know I2 V2, right? I don't know turns. There is no information about turns, so I can use equations related to turns here. But I know I2 V2, I know V1, and I can use the information that for an ideal transformers, we always assume our transformers are ideal. Power 1 is equal to power 2. That tells me I1 V1 is equal to I2 V2 I know everyone else but I1, so I'm going to solve for it. Divide each side by V1, right? This is a simple algebra here, V1. And I will have from here, I should do blue again here. I lost my color coordinates. Alright, I1 here is equal to I2 times V2 divided by V1. And we're done. I2 is 4.17 amperes. V2 is 12 volts divided by V1, 120 volts. We cancel volts. Amperes is left, and the answer is 0.417 amperes, or about 0.42 amperes. Alright, that's it. These two questions are primarily good examples of showing us how much we need to know about AC current, power, and transformers.